Good morning. Steve Morse here with the End is Far. And I just wanted to give you all some food for thought regarding climate change. I'm going to be switching up subjects here a little bit here and there, but today we're going to talk about climate change. So one of the things that I've been pondering is this idea that you can trap 2 watts per meter squared. Sorry. Um, so what we have right here, let me show you here. So this right here is a column of air 12,000 meters high. And what that is that's the average height of the troposphere. That's where 80% of the atmosphere is. And uh, it's where all convection takes place. So right down here where the blue, the green, and the red lines meet, that's the surface of the Earth. So let's go down there and take a look at what we have going on here. So what we have here is this is the surface, this red line and the green line, and this is all air. And what I'm saying here is I'm calculating out how many joules. Let me move this out of the way. The average temperature of the Earth's surface is 15 C. That's 288.15 degrees Kelvin. At sea level, we have a density of 1.225 kilograms per cubic meter. This is for dry air. This is at 1 atmosphere, 14.7 pounds per square inch, I think it is. And what I've done here is I've calculated how much energy it would take to raise 1.225 kilograms of dry air from 0 degrees Kelvin up to 15 degrees Celsius. And that will tell us how much energy density we have here. And that's 354,219 joules per meter cubed. And then what I'm showing here is this is water, seawater below it. And seawater has a slightly less specific heat than freshwater. And this is a ton of material. I don't have all the rest of the data here that I'm showing up here, but what we have in a cubic meter of water at 15 degrees Celsius is 1.137 billion joules. So I was thinking about how much energy is in this column of air. And the reason I was thinking that is because I keep on hearing that CO2 traps 2 watts per meter squared, and I'm just, we don't live in a two-dimensional universe. So I don't believe that you can trap energy in a two-dimensional space. I mean, there's nothing there. So what I'm showing here is that this is just a two-dimensional plane. And what the climate scientists are saying is that there's an average of 1,361 watts per meter squared coming into the atmosphere from space. And they say from top of atmosphere. So that's really at like 100 kilometers or 100,000 meters. So I was trying to build this column with 100,000 cubic meters going up, but it kept on crapping out on me. I think I've got too many things open, or I just don't have a powerful enough computer. So we're just going to go with the top of the troposphere for this conversation. But so we have 354,000 joules per meter cubed at the sea level. And up here at the top of the tropopause, we have an air density of 0.323615 kilograms. And we're at 0.2 ATM because 80% of the atmosphere is below and 20% is above. And if you do the calculations out what we show here is that this cubic meter of air right here has 70,843. So I may be wrong on this, and this is something where I want to get some comments from you folks. But um, what I did is I took 354,219, and this is an interesting number. I'll show you something else here that's pretty interesting. Plus 7,000, 70,843, enter. I'm going to divide by 2. Okay, so the average number of joules per meter cubed in this column should be around 212,531. Now, if you multiply that by 12,000, we end up with about 2.5 billion joules per 12,000 meters cubed. And I added in the 1 meter of water at the very bottom, just because that's part of really the surface. So we end up with around 3.6 billion joules per 12,000. That's really 12,001 meters cubed, because we're including the surface water. So what we're really doing is we're trapping 2 watts. Now, a watt is a joule per second. So you can see that, I've got this number right here, 31,536,000. Well, that's the number of seconds in a year. So if we take that number, we multiply it by 2, we get 63 million extra joules. That's over the course of a year. Now, you can kind of see what's going on here, in that this is very, very negligible. Now, before I go too much deeper into this, I'd like to get your comments, and is this model flawed? Is it somewhat accurate? And can we make any predictions with it? So again, this is the entire column of air. And I do want to show you something else. Hopefully I can find it pretty quickly. Bear with me. Yeah, here it is. This is pretty interesting. So one of the things that I've figured out while I was playing around with how many joules are in a cubic meter of air at sea level is that no matter what the temperature is, the number of joules per meter cubed is almost the same, almost exactly the same. So at 50 degrees Celsius, what we find is that the mass, the density of air at sea level is 1.09 kilograms per meter cubed. And if you do out the calculation to find out how many joules it takes to raise 1.09 kilograms of dry air to 50 degrees Celsius, it's 354,218.65 joules. 40 degrees Celsius, there's a little bit more mass, because there's as the temperature drops, the density increases. And we end up with 354,218 and 0.12. And 30, again, it's very similar. 20 degrees, 15 degrees Celsius, which is the average temperature of the surface, 354,219. And lo and behold, if we go down to, minus 58 degrees, we end up with 354,218. So I think that the reason that these numbers are slightly off is because, I'm not going out far enough with my mass or some other rounding error. But you can see I'm going out several places and we end up with 354,000. Now that's a really interesting thing to me, because what that means is that no matter where you are on the planet, no matter what the temperature is here at the base, going up to the tropopause or beyond, what we would find is that the number of joules that are in the column of air, well, no, that's not true. Let me back up here for a minute, because we have really at the equator we have around 18,000 meters cubed, and at the poles we have around 6,000. So, I'm gonna ponder on that a little bit, but let me know what you think about this, because this has some major implications for the climate theories that are out there, and that is that if you're only trapping 60 million joules amongst 3.6 billion over the course of a year, what are you actually adding? You're not adding very much. And, that's assuming that there's a constant heating and no cooling. So I'm going to finish up there, but I just wanted to give you some food for thought here and get your ideas. I got some other things I'm going to try to figure out photosynthesis as well, because, energy can't be created nor destroyed. So whenever plants convert energy into sugars, that's energy coming into the Earth's system that is not going to go back out as heat. It's being stored as a sugar. So that's something else to think about. Now, one of the things that I think people were going to say is, well, oh, that's not very much. But when you consider that there's 450, I think it's 450 billion gigatons of plant matter. I mean, that's a lot of plants that are converting heat energy, light energy, into chemical energy. So, in any event, we'll look at that in another video. So, I hope that this has caused you to think a little bit, and just remember that the end is far.